The last equilibria that I want to talk about in chapter 6 is just a brief review of acid-base equilibria. We'll go over this in a lot more detail as we proceed in this class, but just as a reminder, when we're talking about acids and bases, what do we mean? So first, what is an acid? There are a few different answers to this. The answer we'll go with in this class is that an acid is a proton donor. So this is something that if we will typically write an acid something like this, H, complex to something or bonded to something, and that will donate a proton into solution, leaving behind A minus. Now we have weak acids versus strong acids, and we'll talk about both of those. In a strong acid, this is not really an equilibrium, it's a complete dissociation. So it's like a soluble salt. These completely separate, something like HCl, hydrochloric acid. A weak acid only partially dissociates. And in some cases, it can be not very much at all dissociates. So something like acetic acid is a very common example of a weak acid. If a acid is a proton donor, what is a base? A base is a proton acceptor. One of the most important proton acceptors is hydroxide. So a hydroxide ion plus a H plus ion will form water. And that's one of the most important reactions in acid-base chemistry. But it can also be something like ammonia. NH3 will take on a proton and form NH4 plus. And many bases are things that dissociate and form hydroxide for strong bases, something like sodium hydroxide will dissociate completely into sodium and hydroxide ions, and then hydroxide is a strong base and will react with any protons, accept them, and form water. Okay, so a base is a proton acceptor, a acid is a proton donor. Now, one of the most important acid-base reactions, and one that we'll keep track of as we're thinking about acid-base chemistry, is water. Water itself is can act as either an acid or a base. So it can donate protons or it can accept protons. And one of the most important reactions is water reacting with itself in equilibrium to form H3O plus OH minus. So H3O plus being a proton donor, OH minus being a proton acceptor. We often will just write this as H plus, but in reality, the protons in solution are surrounded by other water molecules. They don't really exist on their own. But as a shorthand, we will call a free proton just H plus. And the equilibrium constant associated with this reaction, which is known as autoprotolysis of water, is the concentration of protons times the concentration of hydroxide. And at room temperature, this is approximately equal to 1 times 10 to the negative 14. This value is pretty important. So this is, again, specifically at room temperature at about 25 degrees Celsius. This is temperature dependent like all equilibrium constants are. And then one of the important properties that we consider when we think about acid-base chemistry, and again, this is a really brief introduction, we'll go into a lot more detail in later chapters, is pH. And pH we define as the negative log base 10 of the concentration of H plus. And I'll say this is approximate. The exact definition is that it's the negative log base 10 of the activity of H plus. We'll introduce the idea of activity in chapter 8. But this is This is a way of keeping track. The concentration of H plus changes on orders of magnitude as reactions happen, and so we need to keep track of it in a way that's easier. And so this allows us to track very large differences in concentration from things on the order of 0.1 molar all the way down to like 10 to the negative 14 molar. Right, and so this is the scale that we use So right, and just as a reminder of the pH scale, pH 7 is neutral, neither basic nor acidic. Low pH, so as we go down to like 1 or lower, this is acidic. As we increase up to 14 and possibly even higher, this is, my hand moved that, this is basic. And each change of one value in the pH scale is a 10 times change in the concentration of H+. So, you know, changing from pH 7 to 8 is a pretty drastic change in concentration. It's a tenfold change.